We've defined what conditional probability is. It's this equation here. The probability of A given B is probability of A intersect B divided by the probability of B. So given B, here's B, there's B. Given B, what's the probability of A? Well, it's the intersection of A and B divided by B, because B is given. And in a little bit, we'll just multiply this both sides by probability of B, and we'll say, hey, if you give us this and this, we can find that. It's called the multiplicative rule. Let's look at a few examples just to get you going on this. And these are good examples. And basically, it's just pull the numbers out of the problem and plug them into the equation. That's the general idea. Here's a problem where we have some information from a survey on executives who had cheated at golf. That's event A. And executives who had lied in business. That's event B. Well, we know from the survey that 55% of the executives had cheated at golf. So probability of A is equal to 0.55. And from the survey, we have the probability of A intersect B. So they both cheated and lied in business. And that was 0.2. So given these two numbers, we can plug them into the equation and come up with, well, what's the probability of them lying in business given that they cheat in golf? So given that they cheat in golf, which is 0.55, the probability that they lie in business is A and B divided by 0.55, which is 0.364 in this case. So by giving that this event has occurred, you've narrowed the sample space. Here's another nice way to look at these problems. It's in a table form. So in this problem, you're interested in people buying it's farm equipment, I think, and this earth-moving equipment. And so what can happen is that people can either have enough money to buy, or they don't have enough money to buy. Or they can have the desire to buy, or the desire not to buy. And they do some surveys, and they figure out that they think the probabilities are this. In other words, if you've got the money and the desire, then 20% of the time you actually buy, and if you've got the money but you don't have the desire to buy, then only 1% of the time, sorry, 10% of the time do you actually buy. So it reads like that. So this is probabilities of customers to buy. So what we can ask, what they ask is B to buy, given that they have the financing. So they're asking this question: what's the probability that they do buy given that they have the financing? Well, given that they have the financing is this row here. So that's if you say given that they have the financing, well, I don't care about this row here anymore. I only care about that. The probability of given that they have the financing, the probability that they buy is 0.2 out of 0.3, which is the total. The total in this row is 0.3. And so the probability that they buy, given that they have the financing, is equal to 0.2 over 0.3. The probability that they don't buy, given that they've got the financing, is 1/3. So these are very useful. You could also say, given that they have the desire, what's the probability that they're able to finance? So, well, based on this, it looks like it's 2/6. So these tables are a very useful way to look at conditional probabilities. Just to be clear, if you wanted to find out the probability of buying and that they have the financing, that's 0.2. That's just right here. That's an unconditional probability. The probability that they buy and that they have the money to buy. That's a little bit different than saying, given that they have the ability to finance it, what's the probability that they buy? So those are different things. So those tables are very useful. Here's another example where we use the tables to look at conditional probabilities and ask questions. So this has to do with consumer product complaints by the FTC. And so you have a row of during a guarantee period or after a guarantee period, and the different types of complaints, electrical, mechanical, appearance, and then the totals there. And so if you're interested in something like the well, we have to define the events. The event, make sure I say this right, let A represent the event that the cause of a particular complaint is product appearance, so it's that one there. And B represent the event that the complaint occurred during the guarantee period, so this is B, and this is A, it's event B and event A. Then you can calculate things like what's the probability of A given B. So if it's given B, then you've got this row here that totals 63%, and you want the probability of A, appearance, given this row here. Well, it's going to be 32% over 63%, which is 51%. Now this multiplicative rule is simply taking this equation here, probability of B given A is equal to probability of A and B divided by the probability of A. So that A and that A, they go together. And if you just multiply both sides by the probability of A, you've got probability of A times the probability of A, get this right yet, B given A is equal to the probability of A and B. So that's very easy. That's the multiplicative rule. And where this is useful is sometimes you're given this and you're given this. You just multiply them together and you can come up with that. And that's what this this next problem here does. So you can work through that, and it's pretty straightforward. The next example uses what's called a tree diagram. And this tree diagram can be very helpful with understanding probabilities. In this case, we're talking about selecting workers, and there are 10 workers that we select, and we're going to select 2 of them. And we're interested if these workers are giving illegal deductions to people that apply for welfare. So we have 10 workers, and based on some probabilities, 3/10, that's a 3/10, tend to give illegal contributions, or illegal deductions, sorry, to welfare workers, and 7/10 don't. So we're going to select 2 workers, and this is without replacement, from this pool of 10 workers, and we're interested in what's the probability that both workers selected give illegal deductions. So if you draw a tree diagram, if you select the first worker, there's a 70% chance that they don't give illegal deductions and a 30% chance that they do. And now we have this second event occurring that's dependent on this first event. So if we select a second worker, well, now there's only 9 workers available. And so the probability of selecting a worker that does not is reduced by 1. So it was 7/10. Well, now there's 1 less because I selected 1 here. So now this is 6/9, and this is 3/9. It's 3/9 because here it was 3/10, and I did not select 1 that gave illegal deductions. So I still have 3 left, but I've only got 6 left here because I selected 1 here. So these tree diagrams are very useful in that regard. And if I want the probability of selecting 2 that do not give illegal deductions, I multiply these together, 7/10 times 6/9. So this is the probability of selecting one that doesn't give illegal deductions. Here's the probability of selecting another one that doesn't give illegal deductions. These are different, and this is, if I multiply them together, I get both. Here's the probability of the first one does not and the second one does. Here's the probability of the first one does give illegal and the second one does not. And here's the probability that they both do. So it's 3/10, and now here I've already selected one, that's a 2, so that's 2/9. So these tree diagrams can be helpful for having you understand what's going on. An independent event is when the probability of something occurring doesn't affect this other probability. So the book states that event B has occurred will not alter the probability of event A at all. And you can test this with this little equation. If A given B is the same as the probability of A, then they're independent events. And if they're not independent, then they are dependent. So the probability of A is dependent upon whether B has occurred. But this is the test for independence. And here's a little example where it looks like, well, in this case, there are an intersection of events A and B, but if you do the calculations, the probability of A is this, the probability of B is this, the probability of A intersect B is 2 divided by 5. Is that right? 1, 2, 1, 2, 3, 4, 5, 6. So it's 2/6 or 1/3. And if you do the calculations, A given B is 1/2. Well, that's the same as the probability of A, so it doesn't matter whether B is given or not. A and B are independent events. I'm going to skip ahead and do one of these problems, and it's problem 350. So in problem 350, we have this information. We have 3 mutually exclusive events. So if they're mutually exclusive, if you drew a Venn diagram, it might look like that. And these are the probabilities, 0.3, 0.55, and 0.15. So they add up to 1, by the way. So the sum of the probabilities equals 1. Find each of the probabilities. What's the probability of A or B if they're mutually exclusive? Well, you can just add them together. So A or B is going to be 0.85. What's the probability of A and C? A and C, they're mutually exclusive, so it's 0. What's the probability of A given B? Well, they're mutually exclusive. It's 0. If you're given B, there's no overlap, then A is not going to occur. And what's the probability of B or C? B or C, well, you just add them together. That'd be 0.7. Are A, B, and C independent events? No, they're not. They're not independent. If you do the math on that, you will see that they are not independent events.